So in this video I'm going to go through the answers to exercise 1 and exercise 2 from 6.1, which deals with figuring out the shapes and bond angles of different molecules. In order to figure out the shapes and the bond angles, you're going to need to be able to draw a dot and cross diagram, because the shape is dependent on the number of electrons around the central atom, and if you can't draw a dot and cross diagram, you're not going to be able to see the number of electrons that you've got. So the first one I've got here is H2S. My central atom is sulfur. I know that's my central atom because there's only one sulfur, whereas I've got two hydrogens. So I'm going to put sulfur in the center. I'm going to put hydrogen on either side. And now I need to fill in my bonds. Okay, so I need to know how many bonds each of my atoms can form. Okay, so I've written out here a list of rules. And it says that hydrogen can only ever form one bond. That's because it's only got one electron in its outer shell, and its outer shell is the first shell. So hydrogen only ever forms one. Sulfur, down here on the other hand, can form 2, 4, or 6 bonds. Okay, it's in period 3, so it's not capped by having 8 electrons in its outer shell. It can actually hold more, and it can form a different number of bonds. So when I go back here to look at my H2S, I know hydrogen can only form one bond, so that means I'm going to have no double bonds. I'm just going to have a single bond between each hydrogen and my sulfur. Sulfur, however, is in group 6, meaning it's got 6 electrons in its outer shell. At the moment, I'm only showing 2 of its electrons, because it's only forming 2 bonds. That only accounts for 2 of sulfur's 6 electrons. That must mean that it's got another 4 electrons as lone pairs, okay? And I know these electrons are not involved in bonding because hydrogen cannot form more than one bond. So if it's forming just H2S, it cannot use those electrons for bonding. So that gives sulfur 2 bond pairs and 2 lone pairs, meaning it's got a non-linear shape, and the bond angle is going to be 180 degrees. So you're counting the electron pairs around the central atom. The next one I'll look at is BCl3, okay? Boron is in group 3, so again I'm focused on boron because it's my central atom. I've only got one of them, it's my central atom. It's in group 3, and I can see that it's bonded to 3 chlorines. Because it's in group 3, it's only got 3 electrons in its outer shell. Therefore, the maximum numbers of bonds boron can form will be 3. Okay, it can't form more bonds because it doesn't have more than 3 electrons. So all 3 of boron's electrons are already accounted for in those 3 bonds. It doesn't have any left over as lone pairs, meaning it's got 3 bond pairs, and the shape is going to be trigonal planar, and the bond angle is going to be 120 degrees. I'm not worried about the other electrons around chlorine because it's not my central atom. Also, the way I've drawn it here on the page, it doesn't look like the bond angle is 120 degrees. That's fine. Draw your dot and cross diagram just to count your number of bond pairs and lone pairs. It doesn't have to be accurate in terms of the angle that you're saying, as long as you can count your bond pairs and your lone pairs. So in reality, the shape of BCl3, I'd have boron, I'd have a chlorine up there, one down there, and one down there, and you would have at a 120 degree bond angle, but I don't need to show that one. I'm just drawing my dot and cross diagram to work it out. The next one I've got is SiH4. So silicon is in group 4, and it's got 4 electrons in its outer shell. And I can see here that it's bonded to 4 hydrogens, and I know hydrogen can only form one bond. So it's bonded to, 1, 2, 3, 4 hydrogens. It's got 4 electrons in its outer shell, and each of those electrons are involved in forming a bond to hydrogen. I know none of those bonds can be double because A, hydrogen can only form one bond, and B, silicon only has 4 electrons and it's got 4 bonds to form, so it doesn't have any electrons left over to make one of those bonds a double bond. That means I've just got 4 bond pairs around my central atom silicon. That makes its shape tetrahedral, and it makes the bond angle 109.5. So again, the way I've drawn it there is not looking like 109.5. It looks far more like 90 degrees the way I've drawn it. But that's because a tetrahedral molecule is not flat. It's not 2D. It's actually a 3D molecule. In reality, one of those hydrogen atoms will be coming forward and one will be going backwards, allowing you to get this bond angle of 109.5. The next one I've got here is phosphorus. Phosphorus is in group 5. That means it's got 5 electrons in its outer shell, but I can see here that it's only bonding to 3 hydrogens. I know none of those bonds are double because hydrogen can only form one bond. It can't form more than one bond, so there's no chance any of those bonds are double. Therefore, I'm only accounting for 3 electrons when I know phosphorus has 5. Therefore, it must have 2 electrons left over that are not bonding at all. So there's 5 electrons now accounted for, 3 bond pairs, 1 lone pair. That shape is called pyramidal, and it has a bond angle of 107 degrees. Again, that's not shown in my diagram, but it does have a bond angle of 107 degrees. The next one here is a little bit different. I've got H3O+. Oxygen's my central atom. Oxygen's in group 6. It's got 6 electrons in its outer shell. And I've got a few notes written here about oxygen. I'm saying that oxygen can only form 2 bonds because it's a period 2 element and it must have 8 electrons in its outer shell. So I'm saying it can only form 2 bonds, yet here I can see that it's clearly bonded to 3 hydrogens. It's also got a positive charge. This is alerting me straight away that this isn't your typical dot cross diagram. The fact that I've got 3 bonds instead of 2 to oxygen, the fact that I've got that positive charge. So what I'm going to try and do, I'm going to draw oxygen. I'm going to put 3 hydrogens around it, 1, 2, and 3. I'm going to draw these electrons like I draw these bonds as I normally would. Okay, I know hydrogen can only form 1 bond, so I'm just going to draw 3 bonds around oxygen, 1, 2, 3, knowing that hydrogen can only form 1 bond, so knowing that none of those bonds are going to be double. I know oxygen's in group 6. I know it's got 6 electrons in its outer shell. At the moment I've only drawn 3, so that would mean I've got 3 crosses left over. Now there are 2 things wrong with the way I have drawn this that alert me to the fact that I've made some sort of mistake. The first thing I know I've done wrong is when I count the number of electrons in the outer shell. I've got 2, 4, 6, 7, 8, 9. 9 electrons in the outer shell of oxygen. Now oxygen is in period 2 and can have a max of 8 electrons in its outer shell. So it is not okay for oxygen to have 9 electrons in its outer shell. I must have made a mistake. The other thing is, anytime you've got non-bonding electrons, they have to be an even number. They have to sit in pairs. I've got 3 non-bonding electrons. That's not an even number of non-bonding electrons. Again, that is telling me that I've made a mistake. The other thing is I've got this positive charge, and the way I've drawn it at the moment, I'm not accounting for this positive charge. I don't really have anything losing an electron. In fact, I've got oxygen with 9 instead of 8 in its outer shell. So what I've drawn just doesn't match with what I know I should have. So instead, I'm going to draw it like this. I'm going to draw oxygen bonded to 2 hydrogens, as I've seen it do countless times before in water molecules. And then for the 3rd covalent bond, I'm going to make it dative covalent. And a dative covalent bond is a covalent bond where both of the electrons are supplied by the same atom. And in this case, both of those electrons are being supplied by oxygen. That means I've now accounted for 1, 2, 3, 4 of oxygen's 6 electrons, meaning it's just got 2 left. So now I've drawn all 6 of oxygen's electrons, and I've drawn 3 bonds to hydrogens, and you can see that I've got 2, 4, 6, 8 electrons in the outer shell, which is what I should have. My non-bonding electrons, I've got 2 non-bonding electrons, which is a pair, which is what I should have. And I can account for the positive charge, because you'll see in the 2 normal covalent bonds, there's 1 electron from oxygen and 1 from hydrogen. So both oxygen and hydrogen are contributing electron to that bond. But in this bond here, my dative covalent bond, both of those electrons in that bond are coming from oxygen. So oxygen's effectively losing an electron because it's donating 2 electrons to that bond with hydrogen. So that accounts for my positive charge. So this is a dative covalent bond. And again, I was able to spot it because when I drew it without using a dative covalent bond, it was wrong, okay? And that alerted me to the fact that there might be a dative covalent bond in there. if you ever see oxygen forming more than 2 bonds, one of those bonds is going to be dative covalent, because when it's not dative covalent, you end up with 9 electrons, and that cannot happen. So if you see oxygen with 3 bonds instead of the normal 2, and you see it with a positive charge, one of those bonds is always going to be dative covalent. When it comes to working out the shape, I do it the same way as any other. Yes, this is a dative covalent bond, but it's still a bond. So it counts as a bond pair, not a lone pair. So I've got 1, 2, 3 bond pairs. I've got 1 lone pair, 3 bond pairs, 1 lone pair. It's pyramidal, 107, just like what we had above. The next one, pH4. So again, this is another similar situation. I'm seeing a positive charge and I'm seeing 4 bonds to phosphorus, when usually I would see 3 or I would see 5. So if I try and draw it normally with just 4 normal covalent bonds, like so, if I draw it like this, okay, phosphorus is in group 5. It's got 5 electrons in its outer shell. At the moment, I've only accounted for 4 of them, which means I need to have 1 single unpaired electron, okay? I can't have that. I've got 2, 4, 6, 8, 9 electrons in phosphorus's outer shell. Because phosphorus is in period 3, it can have more than 8. It never has 9, but it can have more than 8, so that's not as big a problem as it was at oxygen. But I absolutely cannot have 1 non-bonding electron by itself. So this is wrong. And again, I'm not accounting for that positive charge, drawing it in this way. So again, this is telling me that one of those bonds is likely dative covalent. So if I redraw this again with the 4 hydrogens, and I'm going to draw 3 bonds, just as I did before, with a dot and a cross, and then that final bond I'm going to draw with 2 dots. So now I'm accounting for all 5 of phosphorus's electrons, 1, 2, 3, 4, 5. I don't have a single unpaired electron. I've got 2, 4, 6, 8 in the outer shell, which is looking a lot more familiar, and I can account for that positive charge by the fact that phosphorus is donating both electrons to the covalent bond. It's effectively losing an electron. So that makes it positive. I've got 4 bond pairs around phosphorus. 4 bond pairs is tetrahedral, 109.5. Again, you treat that as a bond pair, not a lone pair, because it is a pair of electrons involved in a bond. The next one, H2F, exactly the same story. Fluorine is in group 7. It only ever forms 1 bond, okay? It only forms 1 bond because it wants to gain 1 electron to have 8 electrons instead of 7. The fact that it's forming 2 bonds instead of 1, the fact that you've got a positive charge, that tells you that one of those bonds must be dative covalent. So when I'm drawing fluorine with 2 hydrogens on each side, I'm making one of those bonds a normal covalent bond. I'm making the other a dative covalent bond. That now accounts for 3 of fluorine's electrons. It's got 7 in its outer shell, so I need to draw another 4. 1, 2, 3, 4. Fluorine now has 2, 4, 6, 8 electrons in its outer shell. I've got the 7 outer shell electrons are accounted for. The non-bonding electrons are in pairs, so I've got 4 non-bonding electrons, so 2 pairs, and I can account for the positive charge because fluorine is contributing 2 electrons to 1 bond. Effectively, it's losing an electron. I've got 2 bond pairs, I've got 2 lone pairs. That makes the shape non-linear, and the bond angle 104.5. I mean, that's not represented in my drawing, but it is 104.5. If you try to draw it with a dot and cross, you're going to end up with an extra unbonded electron sitting by itself. You will also end up with 9 electrons in fluorine's outer shell, and it cannot have that. If it's period 2, the max it can have is 8. Moving on to exercise 2, same story. Question 1 is the same thing again, but in exercise 2 we're going to be encountering some double bonds, which we didn't have in exercise 1. So the first up I've got is beryllium. Beryllium is in group 2, and it's bonding to 2 iodine atoms. Because it's in group 2, it's only got 2 outer shell electrons. Both of those are involved in a bond with iodine, okay? It can't be forming a double bond because it's only got 2 outer shell electrons. It's got 2 iodines to bond with. It doesn't have any electrons left over for double bonds or triple bonds. It also doesn't have any electrons left over for lone pairs. Both electrons have already been used in forming 2 bonds to iodine. Therefore, my shape is linear, and my bond angle is 180 degrees. Now you may actually be surprised to see beryllium forming covalent bonds in the first place. As I said, it's in group 2, So it's a metal, and we're used to seeing metals and non-metals form ionic bonds. Beryllium's actually a bit of an exception. If it was to form an ion, if it was to lose 2 electrons, it would have a positive 2 charge. Magnesium, which is in period 3, is fine with having a positive 2 charge, and calcium in period 4 is fine with having a positive 2 charge. So the other group 2 atoms are fine with having a positive 2 charge, but beryllium is in period 2 and it's small, and it's not okay with having a positive 2 charge. So having 2 plus on such a small atom is actually quite unstable. Lithium, next door, is also in period 2, but it's only got 1 electron to lose, so it's got a +1 charge. Beryllium, equally as small, actually a little bit smaller than lithium, with a +2 charge, is very unstable. So that's just an aside, but beryllium can form covalent bonds even though it's a metal in group 2. Next up, I've got CO2. Carbon's my central atom, so I'm going to draw carbon. I'm going to draw an oxygen on each side. I know carbon is in group 4. It's in group 4. It forms 4 bonds every single time because it's got 4 electrons. It wants to have 8. It's a period 2 element. It must have 8. So it's got 4 electrons. It wants to have 8. It's going to form 4 bonds every single time. And when I look at it, I've only got 2 oxygen atoms. I need to form 4 bonds. I've only got 2 oxygen atoms. That must mean it forms 2 bonds with each oxygen. This works for oxygen too. Oxygen's in group 6. Oxygen must form 2 bonds. Each oxygen is only bonding to carbon, so it must get its 2 bonds purely from carbon. So by forming a double bond between each carbon and each oxygen, you end up with both carbon and oxygen happy. When I've got a double bond like this is where the confusion arises. I don't count it as 1, 2, 3, 4 bond pairs. A double bond counts as 1 bonding region. So I've got 1 bonding region there, 1 bonding region there. 2 bonding regions is linear, 180 degrees, exactly the same as BeI2 above it. Okay, a double bond counts as 1 bonding region. Don't count them as separate bond pairs. Okay, if I've only got 2 atoms, your 2 bonding atoms are going to be as far from each other as possible. They're going to go at a 180 degree angle. They're not going to be any closer than that. The next one, H2CO. So in this one, you might be wondering which one is your central atom. Is it carbon or is it oxygen? Because you've only got 1 of each of them. In order to figure that out, you look at how many bonds that they can form. Oxygen can only form 2, carbon can form 4. You always put the atom that can form the most bonds at the center. Okay? If I try to put oxygen at the center, it can only form, so if I tried, oxygen can only form 2 bonds, and I'd have to bond a carbon to it, and I'd have to bond 2 hydrogens to it, okay, so it's not going to work. So I'm going to put carbon in the center instead, because it can form more bonds. I'm going to arrange the oxygen and the 2 hydrogens around it. I know hydrogen can only form 1 bond, that's it, absolutely max. So I'm going to draw 1 bond between hydrogen and each of the carbons, between carbon and each of the hydrogens. So that's 2 of carbon's electrons used, and carbon's forming 2 bonds, but I know it needs to form 4. I also know that oxygen needs to form 2. So this works out really well. Carbon wants to form 2 more bonds. Oxygen also wants to form 2, so they form a double bond. So again, when you've got a double bond, it's just 1 bonding region. So I've got 1, 2, 3 bonding regions. That makes it trigonal planar, and the bond angle is 120 degrees. The next one I've got here is CS2. Carbon is my central atom because I've only got 1 carbon and it forms 4 bonds. So I put that in the center. I know carbon needs to form 4 bonds. It's only bonding to 2 atoms. Therefore, it's going to form 2 bonds to each sulfur. Sulfur is fine with that. It's in group 6. And it's happy out to form 2 bonds. That gives you 1, 2 bonding regions around carbon. Again, that makes it linear. Again, the bond angle is 180 degrees. Next up, I've got sulfur. Sulfur is surrounded by 1, 2, 3 oxygens. Again, if I look at my little list, okay, oxygen has got to form 2 bonds, okay? It's in period 2. It has to end up with 8 electrons in its outer shell. So I know oxygen needs to form 2, okay? Sulfur is actually in the same group as oxygen. It's also in group 6. So you might think, well, if oxygen's forming 2 bonds, then surely sulfur is going to be the same. But you have to remember, because sulfur is in period 3 and not period 2, it can actually have up to 18 electrons in its outer shell. So it's not confined to 8 electrons like oxygen is, because it's bigger. It can form 2 and have 8 in its outer shell, or it can form 4, or it can even form 6 bonds. The max it can form is 6 because it's only got 6 electrons in its outer shell, and you can't form more bonds than you've got electrons, but sulfur can form up to 6 bonds. Even though that will give it 12 electrons in its outer shell, that's okay because its outer shell is the third shell and it can hold up to 18. So when I'm drawing this, it's the period 2 element that's going to dictate. So oxygen has got to have 8. And it means that it's going to have to form 2 bonds with sulfur. And each oxygen is going to do the same thing. Each oxygen is going to form 2 bonds with sulfur because it has to. That leaves sulfur with 6 bonds in total, but that's okay. 12 electrons is fine for sulfur. It's in period 3. This gives me 1, 2, 3 bonding regions. That makes the molecule trigonal planar, bond angle of 120 degrees. The next one is just SO2. So again, as I said already, oxygen has to form 2 bonds. So it's going to insist on forming 2 bonds. Sulfur is happy to go along with that. But in this case, sulfur has got 6 electrons in its outer shell, and it's only using 4 of the electrons. Therefore, it must have a lone pair. Okay, so make sure you've got all 6 of sulfur's electrons accounted for. In this case, 4 of them are bonding, 2 non-bonding, giving you 2 bonding regions and 1 lone pair. We don't actually have this as a shape in our table. It would also be bent or non-linear. I'm not exactly sure of the angle. Okay, when we had 2 bonding regions and 2 lone pairs, the angle was 104.5. So with only 1 lone pair, it would be a bigger angle than 104.5. I'm not exactly sure of what that is. It's not a value that you need to know. The next one, NH4+. We have seen nitrogen. It's a period 2 element. It can only form 3 bonds. Yet now I'm saying that there are 4 and there's a positive charge. So again, that's alerting me straight away to the fact that it's likely got a dative covalent bond. So I'm going to draw the 4 hydrogens around nitrogen. I know hydrogen can only form 1 bond, so it's not going to be an issue with double bonds. So I'm going to draw 3 normal covalent bonds. I'm going to make my 4th dative covalent. Okay, and again, I know to do that because nitrogen only forms 3 bonds. Now it's forming 4 and it's got a positive charge. 1 must be dative covalent. That means I've drawn all 5 of my electrons for nitrogen, but I still only have 8 electrons in the outer shell. I'm accounting for the positive charge because nitrogen's donating 2 electrons to that bond. It's effectively losing 1. And there's a positive charge. So nitrogen's got 4 bond pairs. Nitrogen is tetrahedral. The whole molecule is tetrahedral with a bond angle of 109.5. The next one, H2SO4. I mean, this is one that involves a little bit of trial and error in order to draw it. So if I were to draw sulfur in the center, because I've only got 1 of them, and I've got 2 hydrogens and 4 oxygens. So if I was to go 1, 2, 3, 4 oxygens, 2 hydrogens, okay, I'd have 6 bonds around my sulfur. That is okay. Sulfur can form up to 6 bonds because it's got 6 electrons in its outer shell, so it can form 6 bonds, so it's okay from sulfur's point of view. Hydrogen's happy out because hydrogen's only forming 1 bond, but oxygen has got to form 2. It's in period 2, it's in group 6, it has got to form 2 bonds to have 8 electrons in its outer shell. At the moment, all of these oxygens are only forming 1. If I made them all double, then oxygen's happy out. Now it's got its 2 electrons, its 2 bonds, but there's too many bonds for sulfur. Sulfur has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? It can have 10 bonds. There's only 6 electrons in its outer shell. It can't form more bonds than it has an outer electron, so this is wrong. So it's a little bit of trial and error that's required. The more times you see this one, the more you'll remember it. But it's actually only the oxygens that surround the sulfur. And I can have a double bond to 2 of those oxygens and a single bond to 2 of those oxygens. That gives me 1, 2, 3, 4, 5, 6 bonds around sulfur, which is the max it can have. These 2 oxygens are happy, they've got their 2 bonds. These 2 oxygens currently only have 1, but I have not drawn in my hydrogens yet. If I draw a hydrogen on each side of the oxygen, hydrogen's got 1, each oxygen's got 2, sulfur's got 6, everyone is happy. So that's what H2SO4 actually looks like. In terms of the shape, you look at sulfur and you look at the number of bond and lone pairs. So as I can see, it's forming 1, 2, 3, 4, 5, 6 bonds. It's only got 6 electrons, so there's no lone pairs left over. But when I'm counting up, I go 1, 2, 3, 4. I'm counting a double bond as 1 bonding region, 4 bonding regions. It's tetrahedral. It's 109.5. The next one, SF6, sulfur, bonding to 6 fluorines. So I'm going to draw sulfur surrounded by 6 fluorines. Are any of these bonds double? No. Sulfur can only form 6 bonds. It's in group 6, 6 bonding electrons. It can only form 6. So I can't have a double bond. Can fluorine form more than 1? No, it cannot. Okay, fluorine is in group 7, period 2. If it forms 1 bond, it ends up with 8 electrons in its outer shell, and that's the most it can have. So everyone's happy with that arrangement. You've got 6 bond pairs surrounding your sulfur. That is octahedral. And it's a bond angle of 90 degrees. Again, as I've drawn on the paper, it's obviously not looking like 90 degrees, but that's because it's not a flat 2D molecule. You'd have some atoms coming out, you'd have some atoms going back, and overall they arrange themselves to have a bond angle of 90 degrees. The last one, H2CO3. I'm going to put carbon in the centre because carbon can form the most bonds out of hydrogen, carbon, and oxygen, and I've only got 1 carbon. But if I were to do this, oxygen, 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 there's my 3 oxygens, there's my 2 hydrogens. I've now got 5 bonds around carbon. Carbon can have a max of 4, so I know this is wrong. I've also got very unhappy oxygens because oxygen needs to have 2 bonds, so technically each oxygen is going to want a double bond to carbon, putting even more bonds on carbon, making it even less feasible. So this is clearly incorrect. So I'm going to take a similar approach to what I did before, and instead of putting all of the atoms around carbon, I'm just going to put the oxygens. And the reason I'm putting the oxygens and not the hydrogens is, remember, hydrogen can only form 1 bond. So if I tried to go carbon, then hydrogen, then oxygen, hydrogen would need to form 2. It can only form 1. So I'm not going to use hydrogen as like my link between carbon and oxygen, but I can use oxygen as a link between carbon and hydrogen. So I know carbon needs to form 4 bonds. So it could form 1 double bond, but the other 2 bonds must be single. It can only form 4. But luckily, I've got 2 hydrogens I need to fit into this molecule. So the 2 oxygens that currently only have 1 bond, I stick a hydrogen on each side, and they both end up happy too. In terms of shape though, I'm just looking at carbon. I've got 1 bonding region, 2 bonding region, 3 bonding regions, 3 bonding regions, trigonal planar, 120 degrees. It doesn't matter that you've got a double bond, it counts as 1 bonding region, trigonal planar, 120 degrees. So really important that you can draw these diagrams, because once you draw the diagram, you can work out the shape, you can work out the bond angle, and as you're going to see in a later video, you also need this to work out if it is polar or not. So really important that you can work out the shapes of molecules.